All right, we'll get going. Just a couple minutes late, but then it'll be exciting because we're going to coding linearizations. We're going to be using the MATLAB toolbox. Hey, friends. Hope we're live now. That is my hope. Let's see if we are good to go. Great. It seems to be working. Awesome. So let's get started. So today we're going to be coding up linearizations, a direct follow-up on the last lecture. But before we get to that, I do want to talk a little bit about your projects. So let's pull up our notepad here. So as we talked about what our that we're going to have a course project at the end of the class instead of having a final exam. All right. And now that you had a little bit of experience working towards simulating physical systems, a thing you have to do for your project, I think now's the time to actually start thinking about what your group's going to be and what your project's going to be. So what we're going to do is today is the 29th. Okay, so for your group projects, first thing you have to do is select a group. Now, you're all remote today, so I know you're not around to just talk with each other. I'll remind you all of this on Tuesday of next week. So what I want is by Wednesday of next week, I want you all to have a group selected, and we're going to have a Canvas submission, which everyone can submit for which you have one group member submit what your project group is, okay? So Wednesday at 5 p.m., what's your group, okay? And then by the next Monday, actually, I apologize. We're going to make this Tuesday. I apologize. We're going to move it up a little bit. Tuesday at 5 p.m., we want to select a group. You're going to submit that via Canvas. And then by Friday at 5 p.m., next week, okay, you're going to submit 3 project ideas. So we're going to send out the official project description document by the end of this week so you can get the actual rubric and everything. But here's what you would need to be able to do. You have to be able to simulate a system. Then you have to control that system. All right? Okay? And now that so one of the key things that you have to be able to do, you need to be able to know how to do is simulate it. That often is the limiting factor. If you can simulate something, there's lots of ways we can control it. But a lot of the project ideas that people come up with, they don't have an idea how to simulate, right? So you're gonna submit 3 project ideas of something you want to simulate and what you want to control, okay? And you're gonna want to define a couple of aspects of what you want to simulate, okay? And what you want to control. So for instance, you need to know what you want to simulate for these 3 different project ideas. Okay. All right. You're going to want to know what your cost function might look like. Meaning, what are you trying to optimize with the control? This is an optimal control course. What do you want to be best? Okay, do you want it to be an efficient controller? Do you want it to be a fast controller? What would it be? What are the considerations? What are some of the options? How many people per group? We have 3 to 4 per group. Sorry, 3 to 4 per group. 3 to 4 people. If you want to do different numbers than that, you can. We'll have a little comments, section beneath the project group submission where you can say, hey, I want to do a group of 1 because I'm a graduate student. I have this particular project. I just want to do it myself. Just gotta let me know. Okay, so that way we're aware that you're not just picking a group of 1 just because you happen to not find a partner. Otherwise, I'll pair you up. I'll find a way to pair you up. Okay. All right. So 3 to 4. So you want to know any cost functions, maybe any constraints. You're going to want to know what your actuator is. What is the thing, if it's a motor, is it the thing, what's the thing that's going to decide that you can say, hey, I want this much effort. It provides the effort that you can arbitrarily control. What's the control input, right? What's your actuator? These are things that you're going to want to figure out and have good ideas for, and we want that by Friday at 5 p.m. and we'll submit it on Canvas. Okay, so we'll get the projects rolling, because now you are in the middle of your homework where you are simulating physical systems. Okay, so hopefully you're getting some experience and you're starting to get an idea as to the kinds of things you can do with the tools you got right now. Okay. Any questions before we move on to the actual course material today? Okay. All right. So with that, we are going to get started, and we're going to, and hopefully you all are working on your homework. I know some people have made good progress on the homework. I've had a couple people go to my office hours, but there are definitely sometimes people run into debugging issues. So if you haven't started, I highly recommend getting it moving. Okay. This is not the kind of class you want to start the homework at the last minute on. Unless you really know what you're doing. Okay. So with that, we are talking about linearizations. So linearization. We're going to do slightly better with our handwriting. So linearization, and we're going to code it in MATLAB. So we're going to have MATLAB open, and just so you have some time to catch up, just in case you need to do this, I'm going to pull open MATLAB now, which hopefully you can all see reasonably well. This is just our code from last time, but what you need to have installed is something called the symbolic toolbox. And if you need to know if you have the symbolic toolbox installed, you can just go type VER, which version of MATLAB you have, VER, and hit enter. And you hit enter, and voila. You can see these are all the toolboxes I have installed for MATLAB. Here's the versions of MATLAB. I have Simulink. What you need, you want the MATLAB toolbox. You also want the symbolic math toolbox. We have not used that yet in the class, but we'll use it today. All right. And also you want to make sure you have the control system toolbox if you don't have that already installed. If you don't, you can go under add-ons, home, on the upper left-hand corner I just clicked on, and you click on add-ons, okay? And you find your add-ons there if you don't have it already, okay? So if you don't have the optimization tool, the control systems toolbox and the symbolic math toolbox, go grab it. And if you don't have the optimization toolbox, you don't need that for today, but you will in the future. Grab that, okay? All right. So as we go back, so make sure, so that's what we're looking for. All right. Anybody have those already? If not, go grab them. Now, let's go back. We are linearizing our systems. So in general, for our ordinary differential equations, we will have some state space form, which is some x dot of t. This is some function of x of t and u of t. These are our dynamics. This is our dynamics in state space form. Okay. If we have a linear time invariant system, invariance within A, friends, don't screw that up. Or LTI system, we can simplify this to be x dot of t is equal to ax plus bu. X dot is equal to ax plus bu. That's what we're talking about, right? Very simple. Ax of t plus bu of t. How nice, how great. And we had a process of taking this system, which could be nonlinear, right? And turning it into this linear system. All right. So we're going to use MATLAB today to take us through the math that we covered last class to turn it into a nonlinear system to a linear system. And I'm sorry, friends, it's going to be the pendulum, but we're going to make it fun. We're going to take the pendulum, but we're going to make it fashion. Fashion. So because we're going to linearize it, all right? So, so today we're going to linearize the pendulum dynamics automatically using the symbolic toolbox. Now, using the symbolic toolbox is honestly, it's a revelation. If you never used the symbolic toolbox for a lot of the tasks in your research life or your homework life, it's a great tool to be able to use. And MATLAB is obviously not the only symbolic toolbox out there. Mathematica is a very popular one for more mathematically focused people who are like mathematicians. So, and there are many others out there, the computer algebra packages. So basically, whenever we're taking those symbolic derivatives to come up with our linearization, it's nice if you don't have to come up with those by hand, especially if your equations start to get long, right? So I'm going to show you today how to do that. So symbolic toolbox. So let's start. Let's refresh ourselves of what the linearization process was. Okay. Step one, for linearization, we had to find we had to choose a fixed point, I should say. Choose a fixed point. A fixed point. Now, a fixed point, as we recall, it's a fixed point is a state such that f of x star and a control input u star equals 0. All the derivatives, so it's a state and input where all state derivatives are 0. Intuitively did this for the pendulum. That's like when the pendulum's up really high at the top, it's just going to sit there until someone nudges it, or at the bottom where it's going to sit there until someone nudges it. Okay, those are examples of fixed points. But as we pointed out, if you change some control input, such as a torque at my finger right here, I can apply a torque that is going to hold that pendulum there. Okay, such that all the derivatives of all the states are 0, since our states for the pendulum are theta and theta dot, angle and angular rotation. Not the angle is not moving, and the velocity is not accelerating. It's a fixed point, right? Step one, you're going to choose a fixed point. And there could be multiple of them, and so as a result, we have to choose them. Okay. Then step two, you want to take the Jacobian. Okay. You would take two Jacobians. One where you take the partial derivative of f of x and u, partial x, that's your state. And friends, I'm going to put a little bar up here up at the top as well. I just put it up there just because I'm trying to be consistent with my bars. I know I'm going to forget some. I apologize. The bars indicating that they can be vectors and are vectors. Okay. You want these two Jacobians. You want that Jacobian, which is your dynamics with respect to your state, x, and your dynamics with respect to your input u. Technically, these should be of time, but I'm running out of patience for that, right? So, and in case you need a reminder, the x state, and the U is an input, in case you need the reminder. Following so far? Not too bad, not too shabby. And then step 3, you want to substitute in your operating point, your fixed point, into these Jacobians. Substitute your fixed point into these Jacobians. Jacobi into these Jacobians. So where the A matrix is partial f of x bar u bar partial x bar. It's your Jacobian with respect to x. Now you substitute in your x star and u star for wherever you see an x and a u. Okay? And your B matrix is extremely similar. It's just the other Jacobian. It's the derivative of x bar u bar partial u bar x star comma u star. All right. Now, remember, the Jacobian is just a fancy derivative. It's a derivative that you do many times because you are taking the derivative of not just a scalar quantity, just one number with respect to another number. There are vectors involved. So as a result, you have a whole matrix of derivatives. So the Jacobian is like a generalization of a derivative. Okay. Now, we did this example with the pendulum. Okay, that's the steps, right? And then as a result, you have A and B. And if you have A and B, you have voila, you have this linear system, x dot of t, say where x dot of t is equal to A x of t plus B u of t. Oh, glory, isn't that wonderful? That's great. Okay. Now, you'll recall, just recall we did this at last class. I won't rederive it just to save us some time, that for the pendulum, where we have our stick of length L with a mass at the end, it's a bob with a theta of t, and it's under gravity, and theta of t is that way. If we have a fixed point of x star, which is going to be theta star and theta dot star, if we decide that it's 0 radians and 0 radians per second, which is at the bottom, whoop, pointed down, and u star, don't forget u star, we have a control input. Let's redo that here. There's a control input, which is a torque of t. That's going to be our control input. It's going to be tau star. Let's say that that is 0 Newton meters. Okay, we have chosen the fixed point, step 1. You'll recall that our A matrix we got out was 0, 1, minus G over L, 0. And your B matrix was 0, 1 over ML squared, like that, right? That was your A and B matrix that we did at the end of last lecture. Lecture notes are online, videos online, if you need to review that. Okay, but we're going to have MATLAB do that math for us, but not quite yet, okay? What we're going to do instead is we're going to code up the result of this linearization and simulate this linear system alongside the nonlinear system. Okay, any questions so far? None? Great, awesome, cool. All right, let's go to MATLAB, my friends. So let's go to MATLAB, my friends. Okay. So we've got here. Make sure everything's going all right. How are we doing today? I'm just gonna take another swig of my coffee. Sorry, I'm an iced coffee guy. I don't care. It's freezing temperatures. I'm always an iced coffee person. Great. All right. We're now at MATLAB. Hopefully you can see this all right. This right now is our code from last time. It was our sim pendulum with control, friends, is what we had. This is the code. This code is also up online. You can download that code. If you have a hard time finding it, let me know. It should be under the files page of the Canvas page. For the folks online, I'll have to put this up on my website so that way people have access to it. I'll put together a GitHub with this at some point. I will get around to that at some point, hopefully soon. All right, so I'm going to make a new folder for today. Going to be 2026-01-29 linearization. Okay. So what I'm going to do is I'm going to take this code from last time. I'm going to make a copy of it because I want to keep this cool pendulum video that I have, right? Because if I run this code, or let's say change folder, if I run this code, you might recall it makes a little, come on, where's the pendulum? Give me my pendulum, guy. Any day now. There you go. This is a pendulum that's being controlled to swing down, okay? All right, if we run it again, you should see it a little faster. Okay, anyone have this code? Anyone able to run this code? You can have an animation and everything, so we can watch what's happening. Nifty. Neat. So I'm going to save this. I'm going to make a new copy. So I'm going to do home. Where I'm going to save. I'm going to copy the file and move it to a new folder. This is not the cleanest way to do new versions, but here's a whole new version, okay, that we can edit for here the 29th. Okay. So right now we have a controller on here for which we have this KP gain. This was our proportional gain that we're using to control our pendulum, our proportional gain. This was our derivative gain. Right now I'm just going to turn those off by making these 0. Proportional and derivative gain right there. And hopefully, folks on the Zoom, you have a clearer view of what's going on, because I found a new technique to broadcast this to Zoom, so you should be able to see things a little clearer. Hopefully that's the case. So, all right, we've got that. So it's still swing. The controller's off, so the thing just swings. There's no control. It just kind of swings around, right? So right now we are simulating the pendulum dynamics, and you'll recall the pendulum dynamics. Let's pull up this here. So these were our linear dynamics. Linear dynamics, where x dot of t is equal to a x of t plus b u of t, where x of t has two states. They were theta of t and theta dot of t. We've done it a bunch of times. I won't try to waste your time with it. And our control input is just tau of t, right? But our nonlinear dynamics, full nonlinear dynamics of our pendulum look like this. They were theta double dot of t is equal to minus g over L sine of theta of t. And when we have a controller, it's plus tau of t over ml squared. We have an actuator on there, a little motor. All right. Nifty cool. Those are our nonlinear dynamics. Now, why linearize? Well, it allows us to do a lot of things like analysis. We talked about, we can analyze this A matrix to tell us how stable the system is. Also, if we know A and B, we can actually make a controller pretty simply for our system. We can actually test if we can even control our system, something called the controllability test that I'll show you real quick today, assuming everything goes well. All right. And you can also generate a feedback controller for U of t to make it converge to a point that you want. So, all right, let's keep moving forward. So let's simulate this system, this linear system here with those two matrices. And let's compare it to our nonlinear system, because the linear system is just an approximation, right? This thing that we did, we basically came up with what we call the small angle approximation, where the pendulum doesn't move very far from the vertical right there, right? Doesn't, if it moves further away, theoretically, the approximation gets worse. Let's show that. Let's compare that, friends. Let's do it. So in order to do that, we're going to need to take our previous code where we simulate the nonlinear system. Now let's simulate the linear system. In fact, what we're going to do for now, we have this whole animation of the pendulum. We're going to comment it out, okay, just for the moment. So everything with create animation for a pendulum, I'm going to highlight all of it, okay, even down through save video. Everything to the end there, I'm going to comment it out. On a PC, I hit Control-R. There are other shortcuts for Mac and Linux that are pretty similar, okay, but it just automatically comments. And if you ever want to uncomment, it's Control-T. So Control-R, Control-T, Control-R, Control-T. Right now, I'll have them all commented. All right. So right now, when I run it, I should just see a plot. And it's a plot that says, here's my angle in radians, here's my time, and here's the ODE45 nonlinear solver. Okay. Well, we can also simulate a linear system. So in order to do that, we're going to need a few things. We're going to define our linear system. Okay. And in order to define our linear system, we need to know our A matrix. Well, we've already figured out our A matrix. It's right here. It's the first row is 0 and 1. So 0, comma 1. This is MATLAB, so the commas are optional, unlike Python. So if you're sticking around for the afternoon, you have to watch Dr. Hibiki fail to remember to add commas. And minus G over L and 0. Okay, that's our A matrix. And we already have G and L defined from the code from last week. Yep, there's G, there's L. Very nice. Okay, now I'm going to make our B matrix. Our B matrix is right there. It is 0 in the first row, semicolon to move to the next row. It's going to be 1 divided by the quantity M times capital L squared. Right? Good. Awesome. So now we have our A and our B matrix defined. We have our initial, so with our A and B matrix, we can actually simulate our system using different tools. We can still use our nonlinear dynamics. In fact, we can do that right now, okay? Right now, here's our dynamics. They are nonlinear. Let's create a linear version. Let's say, hey, dynamics linear. Okay? Linear dynamics underscore lin. Let me make this a little larger, excuse me. So in order to define our dynamics inline, so we don't have to make a whole new file for it. You can always make a new file for it if you want. You say at, creates a function handle, open, close, parenthesis, t and x. So your function needs to take in your time and your state, okay? And needs to return the derivative of both, okay? Here's the thing. Our dynamics, here's the derivative of both, my friends. Derivative of your states is equal to ax plus bu, right? Neat, right? So right now, let's assume that we're not putting any control input in. So let's temporarily knock out b. Let's temporarily say that u is equal to 0. So we'll have the B matrix, but multiply it by its single control input, 0. All right, so therefore the math for this is equal to A times X plus B times U, which is 0. We defined our linear dynamics. Okay. All right, so Now we can use ODE 4.5 to simulate those linear dynamics. You don't need the ODE 4.5. It's overly powerful for this because if you have linear dynamics, there are even better there are faster tools. But we can still use ODE 4.5. That's fine. So we're going to create a new line. We're going to simulate using we're going to simulate using ODE 4.5 of our linear dynamics. It's going to give us our time output vector. I'll call it Tout_lin because it's for our linear dynamics, and our states out. It's going to be X out lin is going to be equal to ODE 4.5 of our linear dynamics. So dynamics lin underscore our time span is from 0 to t final. And we need our initial state, of theta 0 and d theta 0. And we're done. Okay. Now we just need to plot it. Let's try to plot it on the same axes as our nonlinear dynamics. And so I'm just going to do a hold on so that we use the same plot as before. I'm going to plot T out lin, our time points for our linear simulation. Then we have all of our states for our linear simulation. Recall that down the first column are all of our first state, which is theta. That's our first state. So therefore we want every row, colon, comma 1. This gives us all the first column, which is our first state. And we had our red dashes for the nonlinear. Let's just make it a black line, which is K dash, which is the code for a black line. And let's make the line width 3 so it's a little easier to see. Line width of 3. The labels are already on, so let's just hold off. Let's see what happens. See how we did. Here we go. Let me make sure you can see all the code that I just put down. Hey, those look kind of similar, don't they? Would you agree? Anybody getting this? Anybody getting that? Nobody's getting that? Thumbs up, thumbs down. Seeing some thumbs up. Great. Awesome. You'll see they're kind of similar, but they're not exactly similar. They're not exactly the same, right? Why aren't they exactly the same? Because the linearization is an approximation. So what would be some way to test if that's true or not? Like if we're actually approximating right? It's like, well, if we instead of starting further away, which is pi over 4, that's 45 degrees, let's make it like a lot smaller. Let's make it like pi over 10. That's much closer to the vertical. We should have a better approximation. So our initial condition of where we're starting the pendulum, let's start it closer so it doesn't swing as far. The approximation is better. So let's try pi over 10 and rerun it. And look at that. The approximation is better. Now, if we start it further away and it swings further away from our fixed point that we decided, which is the bottom, it should be worse. So let's just try pi. So we got to go further away. So let's start with 9 times pi over, no, let's do pi over 2. That's 90 degrees. So horizontal for the start. Pi over 2. And you can see it gets worse and worse. Now, pi is right up at the top. Now, that's going to be way different. Watch what happens with pi. That's starting the pendulum at the top. What happens? Extremely different. The nonlinear system is just flat, right? It's starting at the top, it stays at the top. But the linear system thinks it's still going to swing. It's really wrong, okay? Let's nudge it ever so slightly off the top. Let's do, minus 0.01, minus 0.1, so we can actually have it swing. You can see how different it is. Here we go. Yeah, you can see that the nonlinear pendulum is going to, wow. Actually, let's animate it so you can see the fun here, okay? You're going to animate. I'm going to uncomment all this stuff so you can see the animation. Okay, I just uncommented all the animation so you can see Wow. Oh, wow. Right? But in figure 1, you can see how different it is from the linear system, right? I know I'm just kind of hitting this with a hammer, right? You can see, look, the linear system is an approximation. You can see how it breaks down as you get further away, right? So now we can actually show, now we can actually show the difference between our linear approximation and our nonlinear approximation, right? I do have to correct one thing. Let's go back to the board. So this making sense so far? We got the A matrix and the B matrix. We did it right. Let's take it back to an initial condition of pi over 4. Pi over 4. And I'm going to re-comment out my animation so we can do some more math without having the animation pop up all the time. Okay, boom. All right. So, all right. So there's one thing I need to clarify. It is true that here we have our linearized dynamics. However, this x here is actually the difference, is the distance from the fixed point. Okay, so I actually need to make a little adjustment here. Okay, I apologize for having to like draw x something out, because right now we're lucky in that our fixed points are 0. Okay, and the linear system, when it's all converged back to 0, it's actually converged back to the fixed point. Here, that fixed point is 0. But what if it isn't 0? Okay, this is actually for the linear system here. These linearized dynamics are actually the dynamics of how it converges or moves away from that fixed point. So here, I'm going to, so what actually I need to do, so cross this out, cross this out, cross this out. And what it is what we call x, I have no space here and I regret it. It's x tilde dot of t is equal to a x tilde of t plus b u tilde of t. Tilde. That tilde, little swiggle, is just to indicate it's the difference between your actual state and your fixed point. So x tilde of t is equal to your state x of t minus your fixed point x star. Okay, and the same thing for u of t. U tilde of t is equal to u of t minus u star. Not something I clarified at the end of the last lecture. I should have done a better job. Okay, but so that's important because we are linearizing about our fixed point. And when you look at this equation with the linear dynamics, okay, that when x is 0, for instance, and b is 0, your derivative is 0. Mean it has to stay at that fixed point. And so, and it will converge back to this x tilde of 0. And so if your fixed point isn't 0, if you didn't do this operation, your linearization will be wrong. Okay, that doesn't matter right now for this current fixed point that we're looking at here. Sorry if it's a little confusing here, because our pendulum's at the bottom, where theta equals 0. But what if theta equals pi? Okay, and I'll show you what I mean. So let's go to our other linearization. All right. So our other linearization, which for our other fixed point, I should say, for when the pendulum is at the top. Okay. So fixed point for the inverted pendulum, meaning it's upside down. Okay. Where this angle here, theta star, is equal to pi radians. And theta dot star, which is the speed, it's in radians per second. and tau star is still going to be 0. Not going to be pushing it, right? We derived last time that A is equal to 0, 1, positive G over L, 0, and B was the same. 1 and, sorry, 0. Oh, I did it again. I did the exact same mistake as last time. 0, 1 over ml squared. I don't know what neurons fire in my brain to try to put a 1 there, but they did. Okay. And our nonlinear dynamic, and our linearized dynamics are x tilde dot is equal to A x tilde, these are of t, I'm sorry, of t, plus B u tilde of t. Now knowing that x tilde is equal to your actual state minus x star, and u tilde of t is equal to u of t minus u star. So how does this affect our math? So let's write, okay, go back to our math here. So let's change our dynamics, our fixed point. We're going to define our fixed point. Fixed point. We're going to call it x star. Let's first keep it at 0, 0. This was our down point, just to show that all the math will still work. And u star is 0. This is our non-inverted pendulum, straight down. And the nonlinear, and now our linear dynamics are, instead of x, it is x minus x star. Right there. Let's get that. Right. X minus x star goes in there, plus u, which is 0, minus u star, which is currently also 0. Okay. Now that works, but this will give you the dynamics in terms of x tilde. So if this here, that comes out of our simulation, we are simulating the dynamics of x tilde. Okay. See how this works. All right. And we also have to take our initial condition and subtract out x star. See how this works. X star. And then when we are done, we have to add in x star plus 1. Excuse me. Okay. Give me a second. They're making a small mistake. I apologize. I'll go back and explain this. Get this right. Ax, we're simulating x tilde. So I'm going to get rid of this. I'm going to get rid of this. And we're going to keep it this here. I'm going to check and make sure this all works here. Okay, that still works. Apologies while I do a little bit of fudging around. What I'm trying to do is I'm making sure I'm subtracting x star from the right places, and I'll clarify what. Because the dynamics of this system are the dynamics of x tilde, right? So it means our initial conditions here are in terms of x tilde, which is x minus x star. So as a result, we have to give it the initial conditions, but these dynamics are in terms of x tilde. So with this here, this output, these dynamics here, these are, we'll call that x tilde out linearization, because they're linearized, okay? And that means that these angles that are coming out are the angles with the fixed point subtracted out. So if we have a fixed point that's something other than 0, we have to add it back in, which is x star 1. So that's our fixed point. So this should all still work for our pendulum starting at the bottom, okay? Now I'm going to move our fixed point to be the top. So this is now pi. This is now our new fixed point. This is now at the top, okay? Now if we change our initial condition. Let's change it to something very close to the top. So let's make it pi minus 0.01. So we're starting near our fixed point at the top. Now we know things are going to go horribly wrong. It's going to go off to the side. It's going to fall. But the linearization, if it's correct, should depict that. So what changed with our linearization? There's a matrix. Here we go. For our pendulum that's straight up, we now have a positive G over L right there. So we have to change right here, this negative to a positive. Okay, right there. That's now a positive G over L. Okay. And I'm going to change the T final to be a much shorter period of time because it's going to go crazy. Okay. So we're going to change our T final from 5 seconds. Let's change it to half a second. 0.5. 0.5 right there. I'm going to run it. See what happens. Okay. Can I even see the ODE solver? I can't see it very well. Okay. I'm going to go for a longer period of time. Let me try 2 seconds. Here we go. Now we're talking, my friends. Okay. I'm going to change the T final. Let's change it back to 5 seconds. See what happens. Okay, that's too much. It's too much. I'm going to change it to 3 seconds. 2.5 seconds. Playing around here. All right. You can see that the angles, they start near about 3.14. It's about pi, right? Near the top. And the ODE 45 solver, let's change the let's change the legend here. The legend is not good. Let's go for where the legend is. Legend, I'm going to move it. I'm going to move my legend till the end. I'm going to say the legend has 2 elements. It's got the nonlinear system and the linearized system. Okay. So it's labeled properly. So the dashed lines are nonlinear system. You can see that the pendulum is going to fall coming down, but then it's going to start slowing down. The linearized system falls off and keeps going off to infinity. It doesn't understand what's happening far away from the fixed point, which is at the top. It doesn't know what's happening down below. It's all linearizing about the dynamics up here, and it will never swing back. Okay. Whereas this nonlinear system will eventually swing back. Is anyone getting this? Is anyone getting these this result, or does anyone need to see the changes that we made? I can go over them real quick. It's just the initial conditions. I made them very, very close to pi minus 0.01. I changed the x star here to pi. This is our fixed point in state. This is our fixed point in input. So I made that pi. This is now a positive G over L. This remained the same. We did not have to change that at all. What we did is we changed the initial condition. So we said, hey, our initial condition is actually relative to the fixed point. This is the angle that we want. But here we subtract out x star. That's relative to the fixed point. And then once you're done, you say, great, thanks for giving me x tilde over time. Now add back in the fixed point. Because, as we know, your actual state, x of t is equal to x tilde minus is equal to x tilde. So if you add back in x star, voila, that's what you see there. Any questions about that? Why are we adding x star into the initial? Why are we adding x star to the initial conditions? We are subtracting x star to the initial conditions. And let me just clarify this here, because this wasn't as clear in how I set up the thing here, how I set up the problem. So the linearization, we would all agree, is about being near the fixed point. Okay, how does it behave near the fixed point? And when you're at the fixed point, the derivatives should be 0, right? So your dynamics look like this. X tilde dot, meaning so x tilde, which is the difference between your current state and x star, right? Those are your dynamics. So that means the initial condition, let's say our actual initial condition for state is pi as an angle, right? But our fixed point is also pi as an angle. In terms of what x tilde is interested in, it's equal to x of t minus x star. So here's your initial state, theta and d theta, and subtract out x star. Okay. And then when we're done, we've simulated x tilde, and we all know that x tilde is equal to x of t minus x star. So if you want to know what x of t is, your actual state, it's equal to x tilde of t plus x star. Sorry, it's a little bit crowded. X tilde of t plus x star. Okay, that's so when you're plotting it and you're done, that's your actual state. That's what it is. Can I explain the sign change of G over L term again real quick? Well, it's because, let's go into how MATLAB solves it. So at the very least, because we changed the fixed point, this last step of linearization, where is it? Where you substitute the fixed point into these Jacobians, that fixed point has changed. So in the A matrix, you'll see that there's a cosine in the A matrix. So instead of substituting in theta equals 0, the cosine, you substitute in theta equals pi, which is a -1, and switches the sign, okay? But let's do the MATLAB component because we're running a little low on time. I took longer than I wanted to do that. So that might actually shed some light here. So what we're going to do is we're going to start using the symbolic toolbox to take those derivatives for us, okay? So I'm just going to go into the command window and show you how symbolic toolbox works, okay? As we know in most programming languages, if you say something like, I don't know, a equals 1, it assigns a to be a numeric value 1, right? So if you said, hey, what is a times 2? Tell me. It'll tell you 2, okay? Or so as opposed to if I create a symbolic variable, I'm going to call it sims a. This creates a symbolic variable called a. Behaves differently, okay? So if I said, hey, what's a times 2? It actually says, hey, it's 2a, right? And then you can do math on that. I could say, okay, well, what is a plus a? It'll tell me 2a. What is a plus a squared? It'll give me 4a squared. And you can create other symbolic variables. You can create lowercase b. So you could say, hey, what's a plus b squared? And you know, as a person who took algebra, you know that's the first outer inner last. It's the FOIL. It's a squared plus 2ab plus b squared. Math, and it should agree. And you might say, hey, actually, I want that in an expanded form. Could you give me that answer in expanded form? Expand that answer, please. A squared plus 2ab plus b squared. Okay? You can solve for equations using the symbolic toolbox. It's amazing. Also, you can take derivatives. So I've already defined a as a symbolic variable. How will you know it's a symbolic variable? If you want to know, you can say class, open parenthesis a, and it'll tell you the class of variable that you've created. So if I said class of a, it's a sim, okay? It means a symbolic variable. Whereas if I created a random other variable, c, and I said it's equal to 10, I didn't call it a symbolic variable. So if I say, hey, what's the class of c? It says it's a class double, which is a double precision floating point number. It's a number. It's a real number. Okay, stored with double precision. Okay, so you have to, if you define something as a symbolic variable, you can do other symbolic techniques as well, such as derivatives. So the command for derivative is diff. So if you want to say, hey, I want to know what the derivative of a squared is with respect to a, I say a diff, open parenthesis, a squared, comma a. We know the answer is 2a, and MATLAB agrees, right? Awesome. Yeah, so some people are saying, I wish my calculator can do this. Many calculators can. Make sure it can't. See if it has computer algebra in it, right? Many calculators, even when I was in high school, I had a calculator that did this. So they do that. What's the benefit of that? Well, these Jacobians were just derivatives, right? So we can have MATLAB take a bunch of derivatives, just like we did in class last time. Okay, so in fact, my friends, MATLAB can take Jacobians. The command is Jacobian. Okay, so recalling that the Jacobian make it bigger, is going to be the derivative of some vector. Okay, so let's call it some vector x bar with some vector y bar. Okay, it's going to give you a matrix. Okay, and it was like partial x1, partial y1, where all of the partials across this, this became partial ym, and here is going to be partial x, so partial yn. I'm just writing it differently and quickly just because we're running a little low on time. So partial xn, partial y1, and here's going to be partial xn. This is m, partial y m. Sorry, that was really sloppy, but this here is a 1. That's an m. So this has constant bottoms. This has constant tops. You can have MATLAB take a derivative of a vector with respect to a vector, otherwise called a Jacobian. It's not a big deal. Let's go back to the code. It actually has a command, help Jacobian. The MATLAB command for taking Jacobians is Jacobian. How nice. Makes everything nice. So if I wanted to take the derivative of the vector, so I want to take the Jacobian of the vector a underscore a semicolon b, column vector, with respect to a semicolon b, I know that that is going to give me the partial derivative of x with respect to x, then the partial derivative of x with respect to y, then the partial derivative of y with respect to x, and then the partial derivative of y with respect to y. So this is going to become 1. That's going to become 1. That's going to become 0. That's going to become 0. Let's see if MATLAB agrees. MATLAB agrees. How nice. So we can take derivatives and Jacobians. You can see how our life is going to become very easy once we set this up to do our linearization for us. The angle for my, so someone's saying, hey, the angle for my linearized system is going off to negative 10,000s for some reason. Yes. Shrink your time span. What's your time span? I think ultimately the time span I chose is 2.5. Okay. That's correct. I don't know if it's going off exactly at the rate that it should, but it's an exponential growth for the system. Here, friends, I'm sorry, I'm going to bop around a little bit. Remember, so this A matrix that I came up with, that we have in right, 0, 1, positive G over L, 0. Basically, this A matrix is unstable, meaning it'll go off exponentially. Okay, it's F5. Adam, change it to 2.5. See what happens. Okay, it won't go off as far exponentially, but this is correct. The linearization predicts incorrectly that the pendulum will go off to infinity because it has no concept that sine of theta will bring it back around. Yeah, that's correct. So this A matrix, friends, remember we said if we take the eigenvalues of the A matrix, if it's unstable if any real component of those eigenvalues is positive. 3 is a positive number. EIG took the eigenvalues of A. It predicts it's unstable. Okay. And if we quickly changed A to be equal to 0, 1 minus G over L, 0, the stable version the neutrally stable version, the one at the bottom, minus G over L. Eigenvalues of A, they are on the imaginary axis. And if you took controls and learned about poles, that's an undamped system. It swings forever, just like the pendulum does at the bottom. Cool. So, yep. All right, so we can take Jacobians. That's exactly what we need to do for linearizations. So let's do our own linearization at the very end of this code here. Excuse me. Okay. So you're going to use MATLAB Symbolic Toolbox to linearize for us. Okay. So we've already defined U star and X star. So we need to we defined our fixed point above, which was X star and U star. I'm just pointing out that we need it, but it's already higher in the code, right? And in order to, so that was step 1. Step 2, take the Jacobian of our dynamics with respect to state and input, right? So here's the thing. Our dynamics, as you will recall, needed to look like this, where we had x dot of t is equal to some function of x of t u of t, right? What that looked like, well, we wrote that in code and multiple times in class, where this is going to be what? Theta dot of t, theta double dot of t. In terms of state and input looks like this. Theta dot of t, and then you have minus G over L sine of theta of t, plus, I'm going to put this over here, tau of t over ml squared. This is a vector, which we're then going to take the derivative with respect to a vector, either state theta of t and theta dot of t, and input u of t is equal to tau. Okay, so let's define these vectors in terms of symbolic variables, then take the Jacobian, all right? And use that, because that's step 2 of the linearization process. So how are we going to do this? How are we going to do this? Okay, let's go back to the code. So we need to define, let's define our dynamics and states in terms of symbolic variables. So let's create some, in order to create a symbolic variable, you have to declare it. And one way to do it is you say syms. Here are my symbolic variable, syms. I want a symbolic variable for theta. I'll call it th. And d theta over time, the angular velocity, dth. And our torque, tau. Okay? I've now reassigned it to be a symbolic variable. Okay? Now I can say, hey, I want in fact, you know what I'm going to do? I'm going to do this all in the command window so you can see this happen without even writing out the code. So CLC. So we're going to syms theta, d theta, and tau. Okay. I can create a vector x of t that is a vector of my two now symbolic variables, theta and d theta. I'm going to call it x because I can. X is equal to theta, semicolon, d theta. so that they are in different rows, right? I'm going to hit enter. Hey, X is now a vector which has theta and d theta, one above the other, right? Neat. Guess what? I can also create this vector valued function here. It says it's equal to this. I'm going to say f is equal to a vector, so open bracket, d theta, that term right there, and then semicolon minus g over L. I still have those stored as floating point values, numbers, times sine of theta, and parenthesis plus tau divided by the quantity m times L squared. Voila. Now I have f as a vector and x as a vector. Now what I need are my Jacobians, partial f, partial x, and partial f, partial u. So I can also define u as a vector containing my tau. I can say that u is equal to tau. I can put it in brackets or not. It's not going to make a difference in this case. So if I want to know my Jacobians, I can take a Jacobian of f with respect to x. It's actually suggesting that, right? That's that on the left. Voila. Hey, look at that. Minus 49 over 5, that's 9.8. It's minus g over L. Minus times cosine theta. So if theta is 0, that's a negative value, right? Okay. And the other Jacobian, this partial f, partial u, right there. So Jacobian, I just hit up to bring up the same command, Jacobian of f with respect to u. 0 and 1. That term right there, that 1, that's 1 over ml squared. Mass is 1, L is 1, so 1 over 1 times 1 squared is 1. Okay? Hey, look, guess what? Now our third step is we need to substitute into those Jacobians. What do we substitute in? Our fixed point, right? So that's going to be the third step. So first, the next thing I'm going to do is I'm going to take those terms that I just added in here. I'm just going to say that, hey, x is equal to, you can copy this in from your command window if you like. X was equal to theta and d theta. I'm intentionally not putting in semicolons because then it just prints out everything. You can add semicolons later. It just suppresses the output. U is equal to tau. And f is equal to d theta, comma, minus g divided by L times sine of theta, plus tau divided by quantity ml squared. Okay, and I can take that Jacobian. Then I need to substitute in. I'll call it the Jacobian with respect to x. I'll say is the Jacobian of f with respect to x, and the Jacobian with respect to u is equal to the Jacobian f with respect to u. If I run all that, because I don't have semicolons, it'll just spit out all that stuff to the command window, right? Sorry, right there. There you go. Now, what's the third step? So I took the Jacobians. Take the Jacobians. We have to substitute in now our fixed point. Yep. So how do we substitute in values in MATLAB Symbolic Toolbox? As a cool command, it's called subs for substitute. How does it work? I hit help subs. It gives you all kinds of things you can do. But you give it an expression, the thing that you want to replace, and the thing you're replacing it with. So if I had, for instance, if I create a symbolic variable, I think we still have a. No, we didn't. We cleared everything. So we sims A. I could say, hey, I want to substitute in for A, and wherever I see A, I want to substitute in 2. The answer is 2. Or if wherever I see A cubed, I want to substitute, wherever I see A, I want to substitute in 2. 2 cubed is 8, right? If I put in 2.2, does that work? The thing is, you'll notice also it's doing fractional values. So if you ever want to turn it back into a number that you can do math on, you could say, hey, that answer, I want to turn it into a double. This will typecast it as a double, so now it's going to be 10.6 or whatever. Okay, that's a little bit of just class typing stuff. So we need to and you can do the same thing with vectors, that where you see one vector, you can substitute in another vector. So what we're going to do is say the A matrix is equal to Jacobian with respect to X, but we want to substitute in wherever we see our vector X, which has theta and d theta, we want to put in X star. Okay. And B, so let's see what happens when we run that here. Voila, there's our A matrix. We substituted in 0. You'll notice that we also need to substitute in, technically we have to substitute in our U star as well. Substitute in Jacob, so wherever we had our A matrix, if there's any U's that are left, we say, hey, U, we want U star. Substitute it in. Great, that's actually correct for our current fixed point. The only thing is I like these as floating point numbers, so I'm going to say A is equal to double A. That doesn't mean I'm doubling anything. It just means it's turning it into a floating point value of double precision. So I run that. Hey, A, 0, 1, 9.8, 0. What was our fixed point? Pi and 0. What if I change my fixed point back to 0 and I reran it? What'll happen? It's now negative 9.8. This is the neutrally stable version. Okay? Change it back to pi. It's positive. It's the unstable version. It computed it for us. That's our A matrix. And we do the same thing for the B matrix, right? And we'll finish it up with that, right? The B matrix is the Jacobian with respect to U, the expression on the right there, right? Right? So that's going to be Jack U. We're basically done here. So we're going to substitute in where we had the Jacobian with respect to U. Wherever you see X, you substitute X star. This is all a bit redundant because in this particular example, there are no states in that linearization for B. And then wherever we saw B, if there's any U's left over, you substitute in U star. And if it's still a symbolic variable, let's make it into a floating point number by saying double B. Voila. What's our A matrix A? That's our B matrix B. That's it. We linearized for us. We didn't have to take a single derivative by hand. And that's it. So this is going to be so now we're going to shift to the optimization part of the course. These are the tools that you need to simulate a dynamical system and linearize a dynamical system. There's another way to simulate linear systems that we won't use too much called LSIM. It's covered in Controls 1, but it's just a faster and more principled way to simulate linear systems. You don't have to use it. You can just do what we did here with nonlinear simulation using ODE 4.5. Okay. All right. And that's what we got for today. Thanks for going a minute or two over with me. I appreciate it. Hope you're all doing great. So remember for your projects. So look soon for the Canvas for the Canvas announcement for selecting a group. Please do it by Tuesday at 5 p.m. and we'll get our ideas in by Friday at 5 p.m. All right. Cool. Thanks everybody so much. I'll stick around on the Zoom. Thanks for joining remotely as well. Take care.